Okay, so good morning, everyone. I want to welcome you to another statistical learning class. Of course, the focus today is cross-validation in statistical learning. Before now, I remember on Monday I walk you through the purpose of modeling. Okay, I told you that what determines the metric of evaluation used depends on your intention on whether you want to predict or you want to explain. So the metric of evaluation for model performance that we use when we are explaining is actually different from when prediction is the goal. So today, we want to go into method of that we use in evaluating the performance of our model, okay, that we call the cross validation, in statistical learning. Okay, so in the outline, of course, I'm actually going to focus on the types of cross validation. I'm going to showcase, the weakness and strength of each of the cross validation. So when it comes to evaluating the performance of our model. Okay, so let's get started. And I need you to pay attention. I need you to pay attention. So what we're going to be doing now is very, very crucial. Now, I need you to take a look at this image. Okay, and I actually want to explain what this image represent. I'm going to say it's represent a key statistical concept, okay, that relates bias, okay, and variance. It relates bias and variance, and if we the bias having understanding of the bias and variance, that is very crucial in understanding the way the cross validation work, and not only that, the performance you know uh, uh, evaluation that we want to conduct. Now I'm going to start with this. I want to explain each of the notation. I'm going to start with this guy. That guy is a notation for parameter. It's unknown, and that's what we're looking for. Okay? Parameter is unknown population characteristic value that we seek to determine. Okay? That's a parameter. Theta. Now, if you take a look at, we know what we want, right? Take a look at this guy. It's an estimator. Estimator is a formula or method that we use in when sample is involved. Let me tell you this. The story actually started from trying to figure out the unknown population parameter, theta. And if I want to figure out unknown population parameter, theta, what I need to do is to go into the population and take a sample size. When I take a sample size, okay, then when sample size is involved, estimation is involved. I'm going to say again. When sample size is involved, estimation is involved. So the method that we use in estimation is called estimator. So this guy is an estimator. Estimator is a formula or a method that you use on sample. Does that make sense? Okay. Why using the method on sample? You actually want to use it to estimate the information. You want to use it to estimate the parameter of interest. Now, I'm going to come into the third one. This guy is the value that you got from the estimator. The value you got using the estimator. Don't forget, estimator is a formula or method. The value, the value you got is actually called estimate. So there's a difference between parameter, estimator, and estimate. Okay, now the next thing that I actually want to do now is the way the cross validation work. Okay, the way the cross validation work, we actually going to have what I call, you know, the data set. We want to train, we want actually want to use this estimator on different subsets of data. I'm going to say that again. We want to use estimator on different subsets of data set. I mean, the training data set. Okay. Now, if I work on this set of data, I'm actually going to have a theta cap 1. I'm going to have an estimate. If I go to another set of data, I'm going to have an estimate. Now, if I have, let's say for instance, I have 20 set of data. What do I mean by 20? 20 different data set, like set of data, number one, group one, set of data, group two, okay, set of data, group three, and so on like that. And I use the estimator on in each set of data, I'm actually going to have different value computed. What does that mean? The different value computed, which means the estimate now becomes a random variable because it's going to vary. The estimate that I actually got from the first sample, the first set of data will be different from the one I'm actually going to get from the second set of data and so on like that. Now, because there's a variability in them, I can begin to look at the probability distribution. We don't talk about probability distribution without variation because there's a variation in the estimate. Why do I have variation in the estimate? Because in cross validation, we actually have different subset of training data. Now, in statistical analysis, if I want to have a sense of a probability distribution of data set, what am I going to do graphically? I need an histogram. Does that make sense? If you don't understand, ask questions. Statistics is like a story. Now I'm trying to explain the reason why we have an histogram here. The histogram is to understand the underlying probability distribution of the estimate. The estimate here varies. Does that make sense? Now, if the probability distribution is normal, what we're targeting is a normal structure, then we now look at the center. We're going to look at the center. Okay, if you take a look at this guy now, that is the center. Now, that center now is actually what I call, it's actually this guy. Expected value of that. Expectation means average. It means I'm averaging the estimate that I actually obtain from different data sets. Why am I averaging it? Why am I finding the average? Why not finding the median? Why not finding the mode? I'm finding the mean because the histogram here is showcasing normal distribution. Normal. When distribution is normal, it's symmetric, it has a bear shape, okay, the appropriate measures of a central tendency that we also call measures of location is the mean. And that's why we're taking the expectation of that. Now, let me now tell you this. We're now going to compare the expectation of the estimator with the unknown population parameter. If the expected value of an estimator is equal to the unknown value of parameter, there is no problem of overestimation or underestimation here. It's like you hit the nail on the head. You get what I mean? But situation where there is a gap, if the expected value of an estimator is far from the parameter, then that will induce bias. Does that make sense? Now, what is the meaning of bias? What is the meaning of this in modeling? Okay, now I bias actually mean the implication here is that you have used a model that is too simple. I'm going to say that again. You have used a model that is too simple. You are using a simpler model for complicated data set. That simple model will suffer high bias. Without doing cross validation, there is no way we will be able to know that. The essence of the cross validation is to have split your data set into different subset, and you find an estimate from each subset. You average that. When you average that, then you compare that to the true value of parameter of interest. The moment the expected value of an estimator is far away from the true value of parameter, then there's a problem of high bias. And what high bias means there is underfitting. Your model underfits. Your model oversimplify reality. Reality is complicated, but your model oversimplify complicated situation. And that's an error. That's not good at all. So it means your model will not actually detect the signal, because what you want to detect is the signal. The model was not good, is not good enough to detect the signal. Okay, that is when the expected value of an estimator is far from the parameter, the true value of parameter. As you can see in the picture now, okay, as you can see it in the picture, okay, if the center, look at that, the center is here. But look at the true value of the parameter. You see the true value of the parameter? You see the expected value of an estimator? They are not on the same spot. If they are on the same spot, that's an unbiased. Unbiased. We say the estimator is unbiased when they are on the same spot. But the moment they are not on the same spot, that's a bias. Does that make sense? Okay. Now, we now want to talk about the variance now. Now, let me tell you, how do you think I know there's going to be variance? If I can calculate the average, then I should be able to calculate the variance as well. Give me 1 second. Oh, okay. I think I'm going to write here. You actually have, like I told you the other time, you have an estimate one, okay, from a particular data set, estimate two from another data set, and so on like that. Of course, you were finding the average. You were able to obtain the probability distribution because there's a variation. Okay, if there's a variation, okay, you find the average. Then another thing you want to do is look at them. Look at them. Okay, look at the fluctuations in them. The fact that this guy, the estimate is not the same thing as this estimate, they varies. Then I will need to measure the degree, the extent of fluctuation. The extent of fluctuations in the estimates that you compute from different subsets of data is what we call the variance. is this guy here. Give me 1 second. I'm actually going to write. Can you see that guy? That is a variance. What is he talking about? That's a variance of an estimator. Variance of an estimator. Why am I finding the variance of an estimator? Because an estimator is a random variable. An estimator, it varies. The estimate that come out of that varies from set of data to the other. Okay, so that is the variance. If the degree of fluctuation is so high, I'm going to say that again. If the degree of fluctuation is so high, that is called high variance. Do you know why we normally run into high variance? We run into high variance maybe because we actually want to reduce bias. In the bias, the model is too simple, right? You now add a lot of features in the model to make it complicated, but in the process of doing that, it is more flexible. More flexible. Now the model become more flexible. The model become over parameterized. Sorry, the model become over parameterized. When the model become over parameterized, that will lead to high variance. The problem of high variance. You know what high variance causes? Overfitting. Overfitting. That's high variance, which means your model will perform so excellent on the training data, but your model will perform poorly on the test data, which means your model is not good for generalization. Does that make sense to everyone? Okay, that is a problem with high variance. Without conducting Without conducting cross-validation, there is no way I will be able to know whether a model has high bias or high variance. We're able to know that through cross-validation. And the idea here is, can we have a way to balance? So the cross-validation, we actually navigate a path, for us to be able to balance the bias and variance, balancing bias and variance, of course, that we tell on the test error. That will bring the test error down if we're able to balance the bias and the variance. Now, when model has high bias, the implication, okay, or to in cross validation, high bias actually means your model is too simple. You've used a simple model for complicated reality. And high variance, on the other hand, it means your model is too complicated compared to reality, more complicated compared to reality. Your model is too flexible. Okay, but your reality is simple. The model is complicated. That will lead to high variance that we call overfitting. That is not good at all. Your model will do a great job on training data, but your model will perform poorly on unseen data. Okay, that is what this picture is talking about. I want to go into another picture, and I need you to pay attention now. Okay, I need you to pay attention now. I want to go into another picture. Now, before I go into another picture, any question about this image? Any question? Before I go into another image, is there any question on this image? So like I said, when again, this image, um, actually we're targeting parameter theta is unknown, and in targeting that, we actually have an estimator, and the estimator is a formula that we actually want to use in figuring out, in estimating this parameter, because we need estimator in the first place, because when I want to, obtain the value of a parameter, if I go into the population, I'm not going to use everybody in the population. I'm only going to take a sample. And whenever I take a sample, estimation will be involved. If there's no sample, no estimation. So when I take a sample and estimation is involved, but this time around, by cross validation, I have several subset of data set that I want to train my estimator on. And because of that, if I have 10 different set of data, I'm actually going to have 10 different values of estimates. They're going to vary. Then I need to know the probability distribution of that because it varies. Why do I want to know the probability distribution? Because that will guide me on the measure of central tendency to use, whether to, because I want to find the average. Before I can find the average, I need to first understand the probability distribution of my data set. And that is why we plot in histogram. Histogram is not the only one we can plot. We can also plot a density. We can have a density plot. We can have a stem and leaf plot. There's so many graphical approach, when it comes to, summarizing or quantitative data. Okay, I want to go into another picture now. This is another image, and I need you to pay attention. This particular image represents what I call a bias variance decomposition in the context of predictive modeling, predicting modeling. Bias variance decomposition. Okay, that is what you represent. And let us start. Now, when we want to start, we specify a relationship. This is a model. Can you see that model? Y equal to GS plus the error. If I really want to test my method, if I want to test my approach, okay, what we normally do is, let's say for instance, this guy is from Minnesota. This guy is from Minnesota, right? We already know that this guy is from Minnesota. And we have this guy here is doing a job of identify states people come from. This guy is doing that job. Now, all of us, we know this guy is from Minnesota. We already know, okay? And let's say this guy is the one detecting the state people come from. Not only this guy, we have several of them. Let's say we have 1, 2, and 3. Their job is they dictate the state people come from. Okay, this guy is going to look at this guy. So this guy is like data. It's like data. Okay. Now, this guy can say, "Oh, you are from a state. Maybe you are from Minneapolis." This guy says, "Oh, you are from Minneapolis." This guy is going to say, "You are from Chicago." This guy is going to say, "You are from Wisconsin." Which one is very close? The one that is very close among them is the one that mentioned Minneapolis. The one that is closer to that of Minneapolis, the one that mentioned Wisconsin. Does that make sense? Now, I'm actually seeing this guy as a function, G of S, in that model that we already know. Okay, is known. Okay, and what we actually want to do is we now want to compare a series of modules on that. Okay, now when you take a look at what I have here, okay, the G of S is this guy here, which is the true relationship. The true relationship is that guy. We know the true relationship. Okay, now what we now want to do, we want to use different modules, just like the way, that's what I said the other time, different techniques of detecting, right? Different modules. Now, if you take a look at the different modules, if you take a look at some lines, do you see this guy? It's not that clear. Do you see some lines? Okay, do you see those? There's so many lines. Those are so many modules, okay, that we have applied to series of data, and we actually want to see among those models the one that we match the true functional relationship. Now let me tell you this, what do we do in the end? Okay, we find the average of those model. Look at that, because the model here is an estimate. Do you see a cap on G of S? Okay, the model here is like an estimator. Okay, and if you take a look at okay, I'm going to show you. Those are different. Okay, those are different models. Now, you know what we're going to do? We find the average of them. Different model will give different estimate, right? Then we find the average. The average is the expected value of g of x. Does that make sense? Now, the next thing we're now going to do is comparing. We want to investigate the bias. We want to investigate this. The bias here is the difference between the average of model prediction and the true value. The true value is g of s. Okay, the true value is the g of s. Does that make sense? The estimate is the g prime of x. Now, situation whereby the expected value of the expected value of the estimator, okay, is far from the true value, then there's going to be high bias. Does that make sense? High bias. And because they fluctuate, we can get the variance. Let's take a look at this. We can get the variance, we can get the standard deviation. Of course, you all know the square root of the variance is the standard deviation. And if the model prediction fluctuates so much, we're going to have high variance. Does that make sense? We're actually going to have high variance. So what this picture is just trying to talk about is, we want to estimate a true function, g of s, using different models. And because we have used different models, we find the average of the model. Because the models will give different prediction, the prediction become a random variable. Then we can find the average of prediction. Then we can test whether there's a problem of high variance by trying to compare the expected value of the estimator with the true value. And we can also, investigate the fluctuations of the prediction from different models. If they fluctuate greatly, of course, that will lead to high variance. And of course, you know what high variance mean. High variance lead to overfitting, and the high bias lead to underfitting. Okay, so that is for that. Is there any question on that? And of course, you're going to see some triangle and point. Those are data point. Okay, all of that are data point. Okay, they are data point. Okay, now the next is this. Please, I need you to pay attention. Okay, I need you to pay attention. The true functional relationship here is G of S, and that G of S is the black solid line. Do you see the black solid line? That is a true relationship we want to estimate. But you know what we're doing here? We're actually comparing different flexible models. Okay, there's so many models. We are comparing models at different level of complexity. Does that make sense? We are comparing models at different level of complexity. Okay, now I need you to pay attention to the green one. Do you see the green one? The green one is oscillatory, right? It's most flexible. That green one will overfit. When the model is too flexible, it's actually going to overfit. It's going to have there's going to be issue with variance. You can see that oscillation. The green one will overestimate the function. The green one will actually perform greatly on training data, but perform poorly on the test data. But the pink one, okay, I need you to look at the pink one, okay? Oh my God, the pink one. Okay, let me use my pen now. Okay, the pink one, this guy, okay, that we underfit from what I'm seeing. It's going to underfit. Okay, underfitness is as a result of eye bias. Does that make sense? So it's as a result of eye bias. So just like what I said. Okay, so the green one overfit because of it's more flexible. Okay, it's more flexible. Okay, it's too complicated. Okay, it's going to overfit. Okay, and it means there's gonna be high variance. But the pink one we underfit. Okay, I just want you to understand that. So when you look at the pink one, okay, it is very smooth compared to the oscillatory one. You know what I mean by smooth? Okay, when it is too smooth, it's going to be too simple to detect signal. That's why it underfeed. So here we are comparing different models with the different levels of complexity. Okay, so that is what we're doing. Okay, now just like what I said, if you're dealing with a prediction problem, okay, the text error is mid-square error. We use mid-square error. If it is classification problem, it's going to be a misclassification error. So if a module is too simple, if it is too flexible, the MSE, the training mid-square error will be small, okay, but the test MSE will be huge. Does that make sense? So that is what I mean, okay? And that phenomenon is overfitting, okay, because you have high variance, okay? A situation where it is less flexible, okay, of course, what you actually going to have, okay, is what I described the other time. Now, this is what I want to showcase right now. Before I go into this, when a module has I training MSE and I test MSE, I'm going to say that again. If the mean square error for training is I and the mean square error for test is also large, that's a poor model. That model has issue with, the issue is eye bias. The model is not able to detect any signal at all. Okay, I just want to take note of that. Now, when the training has low MSE and the test has high MSE, then that model has high variance issue. It's going to overfit. Okay, it performed greatly on training, but performed poorly on test. It performed poorly on test. That's why the mean square error for test is high. It performed greatly on training. That's why the mean square error for training is low. But what we actually want is striking a balance. We want to have a low variance. We also have low bias. That's what that is. Now, another thing I want to talk about, moving away from that, is of course, when you want to evaluate the performance of a model, when the interest is on classification, instead of us to use a mean square error, we use a misclassification error. So the mean square error is not appropriate here, okay, when you are looking into a classification problem. And classification problem can be, how do I know I'm working with classification problem? That depends on the nature of the response variable. Response variable has to be categorical, okay, for classification problem. Now, in that case, I'm actually going to have this. I'm going to have an indicator. If yi equal to yi cap, okay, I'm going to label that as 0. If it is not, I'm going to label it as 1. That's that's a category. That is being categorized. Now the error rate now is actually going to be that. I actually want to know the sum of I, okay, where yi not equal to y cap, then when I know the sum, I divide by n. It's more or less, I'm finding the average here. Okay, so that is exactly what we use. Okay, the test error, okay, is actually what you say in equation 8. Okay, the same way that we have training MSc, test MSc, we also have a training misclassification error and test misclassification error. Now I want to go to different type of different types of cross validation. I'm going to discuss 3, and I need you to pay attention here. It's becoming critical now. I need you to pay attention now. Okay, now there are 3 different type of cross validation in statistical learning. Number 1 is validation set approach. Please pay attention. In the validation test approach, what we're going to do is to split that entire data set into 2. One group will be training, the other group will be test, which is a validation set. Now, the intention here is we actually obtain estimate of the function using the training set. I'm going to say that again. We got the estimate of the function, okay, using the training set. Then we can calculate its mean square error if we are dealing with a prediction problem. If it is classification problem, it's going to be misclassification error rate that we're going to find. Now, the model we have trained, okay, we now want to validate the performance of that model on the other group, okay, and we're also going to estimate the mean square error for prediction issue, and of course the misclassification error for classification problem. Now I want to demonstrate this to you. Now please pay attention. Pay attention. Okay, I need you to pay attention. Now you know what I'm interested in. I actually want to predict the blood pressure of my patient based on 2 risk factors, gender and age. And I have the data set here. Please pay attention. Okay, this is my data set. Okay, take a look at that. Now, let me tell you this. Some of you may be wondering, if I have data set, how am I going to split my data set? Some people use 50-50, depending on the size. Some people use 70-30. Okay, 70 for training, 30 for test. But if you take a look at this data set now, okay, I want to showcase the idea of a 50-50 split. You know what I'm going to do? The first thing is my multiple linear regression model. Okay, I'm actually going to estimate the parameters, the linear regression parameter, okay, from training. Now the training is the one in green. Can you see training right now? This guy, the green one. Okay, the green one. That's my training. Can you see that? Which means I'm going to estimate the parameters of the regression, the beta non cap, the beta 1 cap, the beta. I'm going to estimate that. And after that, okay, I did not use you know, validation set yet. I only use the green one. If I want to use the validation set, this is the first thing I'm going to do. Okay, take a look at this. So if I want to use this guy, that's number 1 in the validation set. Okay, I'm actually going to plug in this 0 into where I see age, agenda, and 54 into age. Take a look at this. Can you see that? And don't forget, I've already secured the beta node, the beta 1, and the beta 2 cap. If I plug in that, I'll be able to estimate Y1 cap. I will do the same to the second one. Okay, the second one, the 1 and 42 in my text. And last one to this guy. Take a look at that. Do you see that? How many prediction am I going to have? 3 prediction, because I have 3 sets data, 3 test data. Now, what am I going to do now? I'm actually going to, because I have opportunity, in my test, there's an actual response. The actual response, what I'm going to do now, I'm going to calculate a gap, okay, a square, the square distance between the actual value of the response of the blood pressure and the predicted. That's what I'm doing here. I'll do that. When I do that here, I'm going to add them up. Then I'm going to divide by the number of the set. That is going to give me test MSE. That's why I test MSE. Okay, but you know the issue with what we're doing here? It has advantages that it's very simple and easy to implement. But this actually depends on observations. Okay? So, and that is the reason why we're going to consider another one. Another one is called leave one out cross validation. Leave one out. If I have set of data, I'm not going to split my data set. But what I'm going to do, if I have 20 observation, I'm going to use 19. I'm leaving one out at every. So what I'm going to do right now, in my first split, okay, in my first split, I'm actually, if I have I have y1 up to yn, okay, y1, I have x1, y1, s2, y2. What am I leaving out? I'm excluding x1, y1. Do you see that? Now, when I exclude that, then when I want to do a prediction, then this is the MSE associated. Now, the Y1 here is the original Y1 that I excluded. Does that make sense? It was not part of the training. Okay. And the Y cap 1 is the prediction from the. Now, I'm going to do the same. Okay. To all data. The second one, I'm going to leave out Y2S2. Okay, I will continue to leave out. Does that mean in such a way that that is repeated across all observation? Which means I'm going to get so many MSE, right? I'm going to get so many MSE, right? MSE1, MSE2, MSE3, and so on like that. Okay, and at the end of the day, what am I going to do? I'm actually going to find the average of the MSE. But do you know the issue with this approach? When you have so many observations, this approach is complicated. It's going to take time. And that was why I said it can be computationally expensive over large data set when fitting complex models. Does that make sense? But it has some beautiful advantages. Okay. We use almost all the data set in the fitting. Okay. And in statistics, the law of large number, when you have a lot of data set, the more you are very close to the truth, right? Okay. Now, because of that challenges that we have here now, we now want to go to another one that is more popular that we call K-fold cross-validation. Okay. Now, what we're going to do in that very one is, before I explain that, this guy is going to be in the middle of the test validation approach and the leave out one approach. Now, let me tell you this. Let me quickly, I'm going to show you this now. Okay, let me do it here. For instance, if I split my data into 5, I think I write something. Okay, I think I'm going to write on the board. If I split my data set into 5, please, I need you to pay attention. Let's say K equal to 5. Okay, if K equal to 5, I'm actually going to have Ford 1, Ford 2, Ford 3, Ford 4, Ford 5. We normally encourage that it should be equal, each of the Ford should have equal number of data set. Now, I'm going to train here. Okay, I'm actually going to I'm going to train on Ford. Okay, if I train on Ford 3, 4, and 5, okay, I will test on Ford 1. Look at that. 1 is not here, right? Okay, if I train on Ford 1, 3, 4, and 5, automatically the test will be on Ford 2. This will continue like that. Does that make sense? So that is what we mean by cross validation. Okay. Then after that, on each of that, the moment you have a test on each on that, you're actually going to compute your mean-square error. Then you're going to average it. Does that make sense? You're going to average it. And that is what you're saying here. Okay. You're going to average your mean-square error. Now, the last example, take a look at this. That is what we're trying to perform here. We have 12 observation, right? Okay, if you take a look at the 12 observation, okay, we have Ford 1, Ford 2, Ford 3. How many elements do we have in Ford 1? 4, 4, 4, 4. 4 times 3, 12. Take a look at that. Okay, and we're going to proceed this way. Okay, in the case of that one now, I'm going to have Ford 1, 2, 3. Ford 1 up to 3. Okay, and in this case, I'm going to compute the mean-square error. I'm actually going to have 3 mean-square error in this regard. I'm going to find the average of the mean-square error. And that is how cross-validation work. Now, let me tell you this. This is highly recommended, okay, because the approach is strong. The approach actually use all the data, okay, and that really makes that approach to be one of the best approach in cross validation. But let me tell you this: I'm not going to promise you that in the world everything, something doesn't have disadvantage. It has its own disadvantage too. Okay. Now here I said the validation approach is strongly affected by which observation enter in the training and validation set, and thus it may lead to bias estimate of test error rate. Conversely, they leave out. That is for that is validation approach. Okay, not this one. Okay, conversely, the leave out approach, which was the second one, has almost no bias. Okay, but the K-fold approach is between them. It's between them. Because it's between them, I think it is in a very good statistical position when you are between two different approaches. And that's why the K-fold is actually being preferred. Is there any question for me? A lot to be done in the next assignment. So a lot of computation to be done. So get ready. Okay. Of course, um, the material that I released for to the TA this week actually centered on how, of course, the TA is going to walk you through how to conduct this and out. That is the material for the week. Oh, have you had your lab? When is your lab? When? Yesterday? Oh, okay. You did cross validation, right? You're on the right path. Yep. And is there any question for me? Okay, I've started sharing my video on YouTube, so I'm going to share the link today. What's already on YouTube. If you put my name on YouTube, now this is how to know your class. If you put my name on YouTube, you're going to see, for this class, you're going to see star 4052. For another class, star 5401, and so on like that, okay? In order not to create confusion. Make sure you all stay safe. Have a lovely day. Bye for now, everyone.